I agree with the mechanism that we present there. I have a small objection, disagreement compared with the results we presented, and wanted to say there are practically the same results that the group in Athens already reached in 2005. We can cite there, that's why I mentioned it. I will say a lot about that in my work. But in any case, my objection is that what is actually described there is the new thing that is coming the last 5 years in galactic dynamics is the role of chaotic orbits. And the mechanism behind that is related with the saddle points. Between the end of the bar in energies, and spatially, but I'm speaking about the energies, and L1 and L2, we have other saddle points. Earlier energy, for earlier resonances, 4, 6, etc., 5 to 1. So the mechanism is there. So you have the unstable point, you can find the stable and unstable manifolds, and this happens at regions that are more populated, because they are in earlier energies. So always my concern, and I show that in my papers, is that the role of the unstable orbits at this unstable, the manifolds of these unstable orbits might be, or I believe that are equally or more important. And the other thing that I have is that what about dispersion of velocities? We go to the neighborhood of the periodic orbit and we see how direction is along the stable or unstable manifolds. But depends on the dispersion of the stellar component at the area that will dictate how the particles, so these are atomic Hamiltonian systems, will diffuse. So exactly this will determine if this can support the spiral and to what extent. I stop here, but because I will present more of that in my
I agree that there are more orbits, and you have to take into account that here presented the orbits, the new orbits in the picture. You have to think that this is these galaxies, and you have the circular orbits in the outer parts as well, the regular orbits that are also located in the resonances. These unstable orbits of different resonances that also may play a role here, but we think that these are the measurements that they will need to play the main role. But yes, I agree that there are more, but we haven't went into them yet. And for the dispersion of velocities, I don't know. We just started with this kinematic work here. You can see that the dispersion in the manifold is still quite big. So what happens, I think that the manifolds are there and they guide the motion. So in the equilibrium point, in the saddle point region, I don't know if the dispersion is going to be big enough, or it's going to change energy, or we have to check it.
Okay.
As far as I understand, you have used an orbit-based approach. It means that in this case you can't estimate the possible amplitude of all these features, I mean ring-like features. But let us suppose that the amplitude of these ring-like features is comparable with the amplitude of a bar, especially in the case of a big bar. And in this case, as I understand, you should use a subconsistent approach.
Yes.
And it may change all this picture. And what are possible changes? Because it is known that it's very easy to reproduce, for example, a spiral structure as a response to the bar potential. But it's very difficult to maintain this spiral structure in the case of self-consistent picture. And what are possible amplitudes of all these features?
I don't think, if I understand well, I don't think it's going to change much, because I did the exercise with imposing a spiral potential to so have the axisymmetric bar plus the spiral potential, and it doesn't change. What you can slightly changes is the position of the rotation, can be the position of the equilibrium points, but if you impose like a spiral amplitude, a spiral potential, you're going to obtain a spiral bars. The rings are strong enough to have it self-gravitating and impose a potential, so I don't think it's going to change much.
Simple. have you any general idea on about how all these nice patterns may change after the inclusion, the self-gravity and the third dimension?
With the third dimension, it doesn't change because I have a paper with a three-dimensional bar and I computed the planar manifolds and the vertical manifolds, and they just fall into the planar ones. So we need to project into the plane. It's one inside the other. So the vertical, the three-dimension is not going to change the picture. And the Sagasti is more or less the same as
So perhaps answering this question, self-gravity probably is going to make spiral arms rotating with a different pattern speed. So, and also considering the second bar, there are observational studies that show that if you have two bars, usually they are at random angles. So it means they rotate at different speeds against another pattern speed. It complicates the picture, but whether you have the right
my concern, or what I see like the natural continuation of this work is putting evolving bars. So, but then the picture like kind of changes everything, because then I don't have an autonomous system that's going to be time dependent. I don't have conservation of energy. I don't have equilibrium points. So what we were talking yesterday with Eugene, that they are trying to put time-dependent potentials and kind of sparse it more. Which is perfect, because this is what I'm trying to do, but I don't have time to go into it. But yes, it's natural combination.
You mentioned that the way it's predicted, it should have two parts, it's predicted or it's observed.
It's observed. It's a group from the Canary Islands that used red plants to predict this or to observe the second abdomen.
Chaotic orbits in the third dimension plays a crucial role, not so much close to the Lagrangian points, but earlier inside the bar, provided to the system chaotic orbits that even may reinforce observed structures. We have some in this.
So the effect may be significant to the system.
In earlier distances from the center to the rotation, in between energies.
There's a few issues that I have maybe with the Milky Way model. When you say that you use the quadrupole from 10 and 2000, did you, of course, take into account that when you go inside the radius of the bar, it doesn't exactly reproduce the actual effects, that it has problems with the Q parameter when you do that, as well as the temporal effects that were shown by Fuchs in 2001, with this, which are the problems that Bennett used. There's also some various issues with including two bars at the same time, especially in the Milky Way system. And I'll be talking about those on Friday, so I won't spoil it completely. But there's some very, very clear effects that happen when you try to include both observed bars for the Milky Way, and it causes very difficult problems.
But just concerning the third dimension, the known effect is to make the peanut and the vacuum. So it's a major effect to reinforce chaotic orbits. It's a vertical resonance, but also it's the
Lagrangian points.
but it's not changing the description, the 2D description is present.
Okay, I propose
We can discuss it later.
to make discussion later.
Make a small clarification. Our observations, we actually did find a correlation with the maximum tangential force, but the correlation was strengthened with the position. So we did find that maximum correlation.
No questions? Thank you.